Our next speaker is Vesterinen, researcher from Applied Quantum Electronics Group, VTT, and he's going to talk about swinging up the quantum signal. Please.
Thank you for the introduction. So today I'm going to talk about devices which can swing up or amplify weak quantum signals. And this work has been done in close collaboration with the nanoelectronics teams at VTT. And this is something that motivates me to work on the field of quantum technologies. These are the prospects of a future quantum computer. And it has been discovered that in quantum processors, we can harness quantum mechanical effects to achieve dramatic speed up in solving certain computationally hard problems. And these can range from modeling of chemical reactions and materials. And the outcome of this research can be, for example, better solar panels, biofuels, and pharmaceuticals. And quantum computers also excel in solving some optimization problems, such as those encountered in scheduling and logistics. And as a final example, quantum computers will have implications on cybersecurity. So there is a quantum algorithm that can potentially break the encryption of our data. The general purpose quantum computer does not exist yet, but here is a systems level picture of how it could look like. So at the very top you have those powerful quantum algorithms, and at the bottom we have the physical quantum processor that consists of quantum bits or qubits. And the upper part, or the logical layer, is mainly about software, and the bottom physical layer mainly about hardware. And realization of the software part is somewhere in the distant future, and what people are currently trying to do is make the lower half work as well as possible. And I've drawn here a cycle, an quantum error correction cycle. I must emphasize that these quantum bits are very fragile, and they can very easily lose the quantum information that they hold. So the quantum information can be lost in less than 1 millisecond. And to alleviate this problem, we can repeatedly ask this system of qubits whether any errors have occurred. And that's the readout on the right-hand side of the diagram. And if errors have happened, we very fast apply correcting pulses. And in the rest of my talk, I will focus on quantum limited amplifiers, which are a critical building block in making this error correction cycle work. So quantum limited means that the amplifiers add very little noise, and thanks to this, it's possible to extract the information from the qubits in only a single attempt. Here's an example of a quantum limited amplifier realized at VTT. What you are looking at here is a silicon chip with the size of 5 millimeters by 5 millimeters. And it's a so-called traveling wave amplifier, which belongs to the class of parametrically pumped amplifiers. And to understand how those work, we can think whether there is a simple analogy available. So think about a swing. Even children can easily learn how to accelerate a swing. And we who know about science and engineering know how to mathematically formulate this as a mechanical system. And to accelerate the swing or a pendulum, we have to change the length of the pendulum at the right frequency and phase. And to be specific, we would change the length at twice the natural frequency of this pendulum. And kind of a similar principle applies to our parametric amplifier. So it's an electrical device, and by applying a strong microwave pump tone, we change the electrical length of the amplifier at the right frequency and phase. And what kind of toolbox do we need to realize this sort of devices? Of course, we start from the underlying physical principles, and we are building a superconducting amplifier. And here a critical element is a Josephson junction, which in this context is a nonlinear inductive element. And it is this nonlinearity which allows the conversion of the parametric pump power into the power of your weak signal. And we must be experts of micro and nano fabrication. So these devices are realized as many layers of thin films of superconducting, insulating, and metallic materials. And finally, we must have the capability to see if the devices which have come out of the clean room, if they work in practice, and we must know how to carry out microwave measurements at ultra-low temperatures. And here on the left-hand side, yet another micrograph of our Josephson traveling wave parametric amplifiers. It's a device with more than 4,000 of those Josephson junctions. Here you can see 4 junctions per unit cell in this zoom-in. And on the right-hand side is the measured gain or amplification of this very device. So it's providing wideband gain for weak signals in this range of microwave frequencies. And these frequencies are very relevant because that's where the quantum information typically lives. And to conclude, I argue that the quantum limited amplifiers are a key enabling technology for quantum information. And furthermore, more broadly, they are a useful technology for many other applications which similarly require unprecedented sensitivity. And VTT is committed to providing these amplifiers to the QTF community and beyond. I've listed here 2 European Union quantum flagship projects where we also pursue this line of research. Thank you for your attention.
Yes. Do we have some?
Thank you for the nice talk. Could you please give more detailed applications for quantum limited amplifiers? Like what can they be used for quantum technology? Yeah.
So one interesting example is realization of squeezed microwave states. So what I discussed here first was like using those quantum limited amplifiers like on the output side of the quantum computer as an amplifier of weak signals. But we could, like on the input side, generate squeezed states, like non-classical microwave states, which have some applications in quantum illumination, for example. So this is something which the QMIX project is pursuing. And well, it's not only the quantum computer which can benefit from these parametric amplifiers, but also the readout of many sensors. So for example, in the context of this QTF, I can mention the ultra-sensitive nanopolarimeters, like for detection of single microwave photons. And also perhaps readout of quantum dot qubits, which has not been done that much yet with these kind of devices.
Visa, could you say something about the noise temperature of your traveling wave parametric amplifier?
About the noise temperature, yeah, so we have checked does this amplifier improve the signal to noise ratio. Like what we compare against is a semiconductor amplifier, like the one provided by the Low Noise Factory company. And we have seen from 5 to 8 decibels of signal to noise improvement. So I can at least argue that in the noise temperature we are below 1 Kelvin of added noise.
Let's thank the speaker again.